All right, let's look at a circuit. We've already looked at RC circuits, so now we're going to turn our attention to RL circuits. We'll set it up this way. Suppose we have a battery, switch, resistor, and inductor. The battery has some EMF E. Resistor has some resistance R. The inductor has some inductance L. The switch is closed at t equals 0. Before t equals 0, there's no energy in the inductor. There's no current. There's nothing going on here. So what is known are these values here. E is known, R is known, L is known. What is not known is the current. So we need to figure out what the current is. Well, to figure out what the current is, we'll need to go through differential equation. So we're not really going to do that. We'll figure out what the solution looks like and write the differential equation. You need to be able to do that. However, we're not going to go through the steps of solving the differential equation in this case. It's because, a couple of reasons really. The solution to this is going to look an awful lot like an RC circuit. And we did that for an RC circuit. We went through the steps of solving a differential equation for that. However, this is different. It's not exactly the same, so you'll see differences. Also, you probably could figure out what the solution for the current looks like here, just by using your knowledge of the way that these elements work. Let me show you. Let's say that we want to create a graph of current versus time. Now, t equals 0 is when that's closed, and we'll say this goes on to t equals infinity or whatever. But at t equals 0, when the switch is closed, a current is going to begin to flow. And you know, you have a high potential side of a battery and a low potential side of the battery. We've got a path at that point connecting the high to the low, so you expect then there to be a current, a traditional current flow to go around in that way right there. The problem is, or I shouldn't say the problem, however, you'll notice there is an inductor here. And the inductor, if you recall, cannot have an instantaneous change in current through it. So this current that's coming along here, I, is going to go into the inductor, generate a magnetic field inside the inductor, and then that generation is going to form a back EMF, which is going to oppose this current. So initially, when the current comes along here, it's not going to be able to get through the inductor. Eventually, though, the back EMF dies down because the rate of current change is, going to slowly decay. And then what happens is the current is able to go through. So after a long time, the current is able to go through this whole thing, but at least initially, the current is not going to be able to complete its path here. So there will be no current initially. In order for there to be a current at all, the path has to be complete. However, the inductor is effectively a break in the path and doesn't allow the current to go through. So don't think for a minute that you can have a current through the resistor and not through the inductor. It's the same current through both of them. So it's either all or nothing when it comes to the current through each of these elements then. All right, so what does that look like then? Initially, the current is down here at 0. After a long period of time, the current has reached its maximum value, which we'll just call I max up here. And let's draw a dashed line across. So what's that going to look like? That's going to be this rising up, leveling off exponential that you've seen before. So what does that look like? If I were to write the equation then for the current as a function of time, it's going to be I max times 1 minus e to the negative t over tau. Now, of course, tau is going to be different here for the inductor, for the RL case, than it was for the RC case. But you've seen this type of equation before. You know what that looks like just by using your circuits knowledge about the way an inductor behaves. cannot have an instantaneous change in current. The current before t equals 0 was 0. Therefore, the current immediately after t equals 0, when that switch is closed, must also be 0. So the current starts off low and goes high to its maximum value. All right. Now, let's use that same sort of reasoning and let's try to figure out what the voltage is for each of these elements. Let's say the voltage across the resistor versus time. Well, the voltage across the resistor versus time is going to look the same. Now, why is that? Because the voltage across the resistor is just I times R. That's Ohm's law, and that will always apply for a resistor. So if the current looks like this, then the voltage is also going to look like this, because there's a one-to-one relationship between the current and voltage for a resistor. The R here doesn't change over time, it's fixed value. So what does that mean? That means it rises up and levels off as well to some maximum value there, and that maximum value is going to be E. That's the maximum value that the voltage can be across any of these elements. All right, well, what about then the voltage across the inductor versus time? Well, the voltage across the inductor, V sub L, is going to be L di dt. So it's going to be the first derivative of the I here. And if you think through, what's the first derivative? Well, in the first derivative, this one term goes away, and we're left with an exponential term. You know, the derivative of an exponential is going to be an exponential. So the voltage is going to just be an exponential. It's going to be a decaying exponential. Now, let's think that through. At the very beginning, this thing creates a back EMF, and that back EMF opposes the current coming through. So at the very beginning, if I were to put my voltmeter across this, well, then in that case, I'm going to measure a large voltage, and that large voltage is the self-induced back EMF that's opposing the current. But over time, that voltage dies down, and the current comes through. And after a long time, then, the current is coming through here, and this behaves, after a long time, just like a piece of wire. In other words, this might as well not even be here after a long time. So what's the potential across a piece of wire? Well, the voltage across a piece of wire is going to be 0. If you were to put the ends of your probes of your voltmeter across this after a long time, when the current going through it is steady, you're going to read 0 the same way here as if you were to put your probes of your voltmeter here, and here you're going to measure 0. There's 0 voltage then. So what does that mean? That means the voltage across the inductor starts off high at a maximum value, and then over time it decays to nothing. So what does that equation look like? That equation looks like V sub L is going to be some V max times e to the negative t over tau. What does this equation look like? Well, this means V sub R is going to be some V max times 1 minus e to the negative t over tau. So this is the general form of the equation for the voltage across the resistor. This is the general form for the equation for the voltage across the inductor. And this is the general form for the current through everything here. And we figured that out just by reasoning how the voltage across the inductor is going to behave, how the current is going to behave. So far we've really applied no mathematics to this. It's just that we figured out what these graphs should look like. All right, so now let's apply a little mathematics to it. Like I said, we won't go through all of solving a differential equation, but you'll be able to see it, I think. Let's do KVL. KVL. We have one loop here. Everything has the same current. So let's write down our loop equation. I'm going to start in the upper left-hand corner. I'm going to go clockwise here. There's going to be a drop across the resistor, so minus IR. The next thing I encounter is going to be an inductor. There's going to be a drop across the inductor. That's going to be minus L di dt plus E equals 0. There. All right, let's We can put the E on the other side. Everything will have a negative sign. I can just rewrite this as IR plus L di dt is equal to E. There. And we can write this in standard form, di dt. So the first derivative term goes up front, plus I times a coefficient. And that coefficient is going to be R over L is equal to E over L. Like that. Okay, so this is our standard form for the current equation. Now, if you were to go through the steps of solving this, this one is not all that difficult, and someone who's had differential equations would be able to solve this in almost no time. But when you go through the steps, here's what you get. I, and remember I is a function of time, is equal to E over R times 1 minus E to the negative t over tau, where tau is, in this case, is L over R. Okay, so here we have the solution for the current through this, derived mathematically, at least partially mathematically, because we skipped a lot going from here to here. But you can see that it matches up what we have here. So that maximum current is just going to be E over R. That's nothing. If you ignore the time component over here, which the exponential is the only part that has a time in it, so that's the time component. If you ignore the time component, then this is just Ohm's law. I is equal to voltage divided by resistance. Okay, now that we've got that, can we get the voltage across the resistor? Well, the voltage across the resistor is just going to be I times R. So if we take this and multiply it by R, we end up with E times 1 minus E to the negative t over tau. There, we've got V sub R. All right, what about V sub L then? Well, V sub L is L di dt. So it's going to be L times the derivative with respect to time of this E over R times 1 minus E to the negative t over tau. And when we do the multiplication here, let's see what we get. L times the derivative, the first term is going to be 0. The second term is going to be E to the negative t over tau. That negative sign is canceled by when I take the derivative. I'm going to have a negative sign here, multiplied by the derivative of what's up here, which is just going to be 1 over tau, like that. All right, well, what is that? L e to the negative t over tau, but 1 over tau, remember tau is this right here, so this is going to be R over L, and we are dividing by the L's, getting rid of those. So what have we got left? It is, oops, did I leave something out? I forgot my E over R here. And now you see the R's cancel. And what are we left with? E, that's EMF, E multiplied by exponential E times to the negative t over tau. So there's V sub L. And here's V sub R. If you were to graph those two on the same graph, voltage versus time, the V sub R is going to do that. The V sub L is going to do that. And if you were to add them up at each individual time, so let's just pick an arbitrary time here. If you go up here, that's the V sub L curve, and then take that and add it to the V sub R curve, you would discover that those two things added together is equal to E. And that will always be the case, because you know that's the way series components work here. The voltage across this plus the voltage across this is equal to the voltage of the battery. And that's true for any time. So at any time, as long as it's the same time for both components, The voltage across this at that time plus the voltage across this at that time has to equal the voltage across the battery. And that's what this down here shows. That if you, for any specific time, just take the two components, add them together, and it's going to be equal to E there. The other half of that, this is, we have energy being loaded up into the magnetic field in this case, for this RL circuit. We could have the other case where we have energy already present in the RL circuit and it's decaying. Let's talk about that case now. So we'll have a decaying current in this case, and let's set it up this way. Here's the battery. So there's our inductor, here's our resistor. Now we have a switch, and the switch can be either up or the switch can be down. So let's call this the A position and this the B position. And there's our battery. Now, it's up in the A position for a long time before t equals 0. So the switch is thrown downward here at t equals 0. So from A to B at t equals 0. That means that before t equals 0, it's in the A position and there's a current going through the resistor and the inductor. In fact, there's only one current and we have one loop here. So we'll assume it's been in that position for a very long time. So this is going to behave like a piece of wire. It has a nice steady current through it, and that nice steady current has produced a magnetic field internally to the inductor, and all is calm, and we're in a state of equilibrium at that stage. All right, so before t equals 0, this is in a state of equilibrium, but at t equals 0, the switch is thrown. And when the switch is thrown, now the battery has been cut out of the circuit. We have effectively, at that point, reduced the circuit down to a resistor and an inductor after t equals 0, and there's some energy in the inductor inside the magnetic field. And that energy now is going to begin to decay. There's going to be a current that is created here. Let's call that current I. Of course, the resistor is going to radiate away energy at a rate of I squared R, so the energy is leaving the system that way. Well, now if we do the same sort of thing, we end up with a Kvl equation that looks like this. We've got IR plus L di dt equals 0. That's what it looks like when we've got no battery in the system, the way we've got here. Okay, we can write that in standard form as well. I'm not going to do it. You can do that if you want. But let's just jump to the solution. The solution for this is going to be E over R times e to the negative t over tau. Once again, where tau is equal to L over R. All right, so the maximum current is going to be E over R, but it's going to decay over time. So if we were to graph this current versus time, it starts at its maximum value of E over R, which it would be because, remember, before t equals 0, we've got a nice steady current flowing. After t equals 0, the current through the inductor cannot change instantaneously, so it's going to continue for just a little bit and then begin to decay as the resistor radiates away the energy, and there's nothing, like there's no battery to replenish that energy, so it'll eventually decay. So you expect it to do that. That's what this equation describes. And then if we go through the same reasoning, okay, what is the voltage across the resistor? What is the voltage across the inductor? This is going to be I times R. This is going to be L di dt. And you'll discover that this is E times e to the negative t over tau, that it dies at the same rate as this current. And you'll discover that this also is going to be E times e to the negative t over tau. So there is no battery here, so the voltage across this plus the voltage across that has to equal 0. So if one of these is positive, the other one's got to be negative. So you could add a negative sign to one of those, but the point here is that they have the same voltage. The polarity of one of them is going to be reversed, so that whenever you take V sub R plus V sub L, that it equals 0. Okay. All right, now let's work a problem then. Let's suppose we have an inductor, and this inductor has an inductance of 53 millihenry. And it is connected to a resistor of 0.37 ohms. So that's a pretty weird value, but chosen nicely, so the answer comes out nicely. How long, and this is the same situation that we've got, we initially have some energy in the inductor here. Once the switch is closed, then the current begins to flow over here. However, it radiates away at a rate of I squared R. So we've got the situation that we just had. I'm only drawing part of the circuit, but it's this situation. Initially, at t equals 0, there is energy in the magnetic field inside the inductor, and ready, it's after t equals 0, go. Now the question here is, the current is eventually going to decay to nothing. Well, how long before it decays to half of whatever it started with? The equilibrium position is going to be E over R, that's the initial value, times 1/2. Let me say that again. Just to be sure that everybody's on the same page here. The equilibrium value in this case is not going to be 0, even though that is the final stage. The equilibrium value is what it was back here at t equals 0. Remember, before t equals 0, we had that nice steady current flowing through here. That was the equilibrium position. It is not 0 as the equilibrium position. It is whatever that initial current through here was. All right? So the equilibrium position in that case, the equilibrium current is just E over R. And that's half of it. So the question is, how long before it reaches this right here? Half of the equilibrium. Let me say it again. Half of the equilibrium current. All right, well, if we look at the equation for current, it's E over R times 1 minus e to the negative t over tau, like that. And now we need to solve for t out of this. The e over r's will cancel, and we have e to the negative t over tau is going to equal 1/2. All right, let's take a natural log of both sides here. We're left with negative t over tau on the left, and natural log of 1/2 over here. Solve for t. T is going to be minus tau natural log 1/2. This is going to be minus L over R natural log of 1/2. That's what t is. So at this time t, the voltage is going to be half of what it was initially here. I said voltage. I meant current. The current is going to be half of what it was initially here. By the way, at the same time that the current is half, the voltage will also be half. All right. So if we plug in our numbers here, here's what we get. T equals 0.10 seconds. So says the book. I did not check that. You should double check it. But that's so says the book. All right. Let's move on. Previously, when we talked about capacitors, we said that the energy could be stored in the electric field between the plates of the capacitor. And the expression for that energy for a capacitor was U equals 1/2 CV squared. The energy is stored in the electric field. For the electric field to exist, there has to be a potential difference between the plates of the capacitor. In fact, that potential difference has to be maintained if that energy is going to be maintained. Similarly, we can have an energy that is associated with the inductor. Let's call this the energy that's associated with the electric field inside the capacitor. This will be the energy associated with the magnetic field inside the inductor. And that turns out to be 1/2 Li squared, like that. The energy is stored in the magnetic field, but in order for the magnetic field to exist, the current must be present. Now that's paralleled with, in order for the electric field to exist, the potential must be present. The potential difference between the plates must be present. The current here must be present for this to occur. The energy per volume, U, that's a little u here, is equal to big U over the volume, and the volume is the area times the length. This is called the energy density. So the energy density is energy per volume, and it's given by this. So in the case of the inductor, you could say this is going to be 1/2 Li squared divided by A times L. Let's rewrite that. We can group this, the L inductance per length times I squared over 2A, like that. Now specifically for a solenoid, we have L inductance per length is going to be mu naught N squared times the area. So U, little u, becomes mu naught N squared A I squared over 2A, which is 1/2 mu naught N squared I squared. Okay? So there we have an expression for the energy density. But for a solenoid, the magnetic field is mu naught I times N. So U can be written as 1/2 over 1 over mu naught times B squared. Now, I don't remember if we went through that same sort of thing for a capacitor, but if you would have followed through for a capacitor, the energy density is going to be 1/2 epsilon naught E squared. And you can see there's a parallel here. We've got the 1/2 in both of them, the epsilon naught for the electric field, the 1 over mu naught for the magnetic field, and of course the field itself in each of those two cases there. So that's the energy density. For the sake of the completeness of your education, you have now been exposed to the concept of energy density. Another concept that is thrown in here in the textbook is the concept of mutual inductance. Occurs anytime you have two inductors that are close together. Now this is a much more important concept when we start talking about transformers, or when you start talking about circuits that have multiple inductors in them that are nearby each other. Mutual inductance can play a role, but the basic idea is this. Let's say that we have a loop of wire here. This is a solenoid, and we connect this then to a battery. So we've got some current I1 going through these loops here. Now, let's say that we have N1 loops, and this is going to generate magnetic field lines, and you can imagine that the magnetic field lines are going to reach way out into space around here. Well, if we have another coil nearby, let's place it nearby here, and let's hook up to it a galvanometer. And it has N2 for its number of coils here. So we've got coil 1, it's got N1 turns, it's got a current I. That's going to create then some flux. So there's going to be some flux over here at coil 2 due to the presence of coil 1. Imagine magnetic field lines doing something like that. So the field lines from coil 1 are going to interfere with coil 2 over here. Now, as long as those magnetic field lines are not changing, you're not going to have any sort of deflection of the galvanometer. However, if you change this current, if I1 happens to be time varying of any sort, you're going to have some fluctuation in the magnetic field. That means you're going to have some change in flux through these loops, and you're going to get some deflection over here. Okay, this is called mutual inductance, because we have one coil, one inductor that is close to another inductor, and it is influencing that. All right. Now, we'll define the mutual inductance between these two as M. And that is very much like regular inductance. It has a unit of Henry, just like a regular inductor has. And if you want to find out how these two things interact, there's going to be a potential on coil 2 that's equal to minus M times the derivative of the current for coil 1 dt. In other words, there's going to be an EMF set up over here in coil 2 due to the fact that there's a changing magnetic field in coil 1. But that changing magnetic field is due to the change in current, which is what this is. If you look at this, this is just another way to write the relationship between voltage and current for an inductor. Remember, we previously said, well, voltage for an inductor, let's call that V sub L, is equal to L di dt. Okay, well, the negative sign we can put there to indicate direction, just like this indicates a direction as well. But we have an EMF for the second coil that is caused by the change in the first coil, in the current for the first coil. Now, conversely, you also have this. There is a change in the EMF of the first coil due to the mutual inductance for coil 2. So we have then this relationship here. The mutual inductance is due to the fact that there is a coupling between these two inductors. Now later on, like I said, when we start talking about transformers, we may revisit this idea here, but it also applies if you go into a circuits class, a linear circuits class. If you have multiple inductors in the same circuit, it's possible for them to be linked this way through mutual inductance. And that will be an important role because when they're linked, you treat that as if there is just another inductor in the circuit because of that mutual inductance. So you would have an inductance due to this coil, this inductor. You would have an inductance due to this inductor, and then you would have an inductance due to the fact that they're coupled as well. And that will play a more important role whenever we start talking about circuits. So once again, I have presented this without derivation. This is thrown in at the end of this section in the textbook. I present it here for the sake of completeness of your education. Congratulations. All right, now we're going to look at LC circuits. LC circuits are kind of weird because you never see them. In fact, there's no such thing as a pure LC circuit. You almost always are going to have resistance. If nothing else, the resistance of the wires involved here. So we're going to assume that we have a perfect inductor and a perfect capacitor and put them in a circuit with no resistance. So this is sort of a fictitious type of thing, a fictitious type of circuit, but I think it'll be insightful to you. The way we're going to set it up is, let's say that we have a capacitor here and we have an inductor over here. There. Now nothing's going to happen unless there's some energy already present here. So let's imagine that there is an electric field in the capacitor, and then we hook up the capacitor and immediately we have the situation here. So the capacitor has some capacitance, the inductor has some inductance. all of the energy is initially over here in the electric field of the capacitor. And then when the current begins to flow, what's going to happen is there's going to be a magnetic field eventually build up over here, and it's going to reach a maximum value. When that happens, it's not going to stay that way for long because all of the energy has been drained out of the capacitor, has been transferred to the inductor. And at that point, the magnetic field begins to decay, and when the magnetic field begins to decay, it generates a current as well. You remember, it generates an EMF, which is going to cause a current. So the energy transfer goes back to the capacitor at that point. So what's going to happen here is if you put a charged capacitor into this circuit, you're going to see energy transfer from the capacitor to the inductor, from the inductor back to the capacitor, from the capacitor back to the inductor, from the inductor back to the capacitor, and it's going to be a perpetual motion machine. That's why I was saying these sorts of things never really exist, because you're going to lose energy, and it would never be a perpetual motion type of machine. But we're talking about the idealized case here. So the energy starts over here, goes over here, and back and forth and back and forth and back and forth. Now, the energy that's in the electric field is given by 1/2 CV squared, but because we have Q equals CV as the capacitor equation, we can make a substitution down here and write this also as Q squared over 2C. So that's the energy in the electric field. The energy that's in the magnetic field, we can write that as 1/2 L I squared, like that. Now, if there is no resistance here, and the energy is just transferring back and forth and back and forth, then this energy plus this energy at any specific time are going to be a constant. In other words, U sub E plus U sub B is going to be equal to a constant. There is no energy that's being added to the system. There is no energy that's leaving the system. So all of the energy starts off over here initially. So that would be U sub E, and U sub B would be 0 initially. But after a long time, all of the energy has been transferred over here. So all of the energy is now U sub B and no U sub E at that point. And then it's going to be transferred back and forth. So these two things here are going to change with time. It's not that U sub E is constant, because Q changes. Q across the capacitor, the charge across the capacitor, is going to change. So Q is a function of time. I also is the current, and the current is a function of time as well here. It's not that U sub E is constant or that U sub B is constant, it's that the total is constant for a perfect circuit. 1/2 Li squared plus Q squared over 2C has to equal a constant value. Now, another way to say that it's equal to a constant value, if this is the total energy U, another way to say that is that du dt is equal to 0. Because if U, the total energy, is equal to a constant, then of course the first derivative of it is going to be 0. So that's just another way of saying what we just said. The total energy is constant. Okay, well, let's do that. Let's take a derivative, d dt, of all of this stuff right here. All right, let's do that derivative, and let's do it right here. This is going to be Li times di dt. That's the first term. Plus, let's see, the 2 comes down, cancels that 2. This is going to be Q over C times dq dt. And that's equal to 0. All right, now let's make a substitution here. I want you to notice that I is dq dt. That's what current is. That's a definition of current. And then di dt, Well, that's just the second derivative, d squared q dt squared, like that. And when we plug that into this equation, this becomes L I d squared q dt squared plus q over c times I equals 0. All right, now we can divide both sides by I here. As long as I is not 0, that'll be okay, it's legal, and those i's will go away. And we have a differential equation that looks like this. Let's go ahead and write it in its general form, d squared q dt squared plus 1 over LC times q equals 0. There. So we have a solution to this equation. Or I should say, if we can find a solution to this equation, then that is what the charge on the capacitor is going to be. Now, looking at this, this is a different kind of differential equation than you've seen before. This is a second order homogeneous differential equation, and it's more complicated to solve. However, I think you can figure out what the solution should be, because ignore the coefficient here for just a moment and think in these terms. Q is going to be a function, and this is the second derivative of the function. Can you think of any sort of function that when you take the function itself and add the second derivative of that same function together, it equals 0? Can you think of anything like that? Well, exponentials, you might think, would do that, but they won't work in this case. There's another function that will work, and that is sines and cosines. Sines and cosines work. So if you take q equals to some maximum value, big Q, times the cosine of omega t plus phi, there is the solution to that differential equation. In this case, big Q is the amplitude of the oscillation. Omega is the angular frequency, and that really controls how fast it changes, how fast the cosine changes. And then phi is the phase angle. It's a phase constant that controls where in its phase does the cosine start or stop. In other words, it slides the cosine function either left or right in order to align up with the axis or to be off a little bit. So big Q, if I'm looking at a cosine term here, big Q controls whether or not we end up with something like that or something like that. The only difference between these two is the height of the peak, and that's controlled by the big Q. The omega, let's go over here, the omega is controlling the frequency, so that determines whether or not we have this sort of function or this sort of function, a much higher frequency. That should have been a nice steady cosine there. And then this phase angle phi controls where it starts here. In other words, does it start right at 0 and do that? Or does it maybe start back here and then do that? So that's what the phase angle controls. So with these three parameters here, big Q, omega, and phi, you can control the shape of any cosine curve. So these are just general variables that would go with any cosine function. And you can figure out the shape of the answer based upon how those things change there. Now, I have said that this is a solution to our second order differential equation. Let's prove that, because if I take that function and take its second derivative and do this, then yeah, it should equal to 0. So let's take it. Let's begin and just rewrite Q equals big Q cosine omega t plus phi. And now let's take a derivative of that. So the first derivative, dq dt, that's the current, but we're just taking first derivative of it. That's going to be, let's see, big Q, cosine is going to be minus sine of omega t plus phi times the derivative of what's inside the parenthesis, which is just going to be omega. There, that's the first derivative. And now let's take the second derivative. Well, it's going to be minus omega q, sine is just cosine, omega t plus phi, multiplied by the derivative of what's inside, which is another omega, so that changes that to omega squared. All right, there. All right, our equation was this, d squared q dt squared plus q over LC is 0. Well, the second derivative is, let's make some room over here, minus omega squared big Q cosine omega t plus phi plus 1 over LC times Q, and Q was big Q cosine omega t plus phi, and that has to equal 0. All right, well, let's see what we can do here. You'll notice that some things cancel here. The cosine term, first of all, goes away. The Q, big Q, also cancels. And what have I got left? Minus omega squared plus 1 over LC equals 0. So I could write that this way. Omega squared is equal to 1 over LC, or omega is equal to 1 over the square root of LC. Now, that doesn't look too surprising, but here's the point. If omega is equal to 1 over the square root of LC, then this is a true statement. And this is indeed a solution to our second order differential equation if this is the case. Now, what does all that mean? That means if we go back here to our circuit and we figure out what Q is, then we also have figured out what I is. I is just a sine function. So the current in this case is going to look something like that, and it's going to vary over time. The frequency at which it varies is going to be 1 over the square root of LC, and you can choose how fast the oscillation occurs by picking your values of L and C. So when you build the circuit, if you were to build this circuit, it's the L and the C values that you choose that determine how quickly it varies, either slowly or fast. All right. So those LC values then are the thing that cause the oscillation. Remember, RL and RC circuits, there was no oscillation. It was straight decay or rise and level off. Here with LC together, we have an oscillation. Now, we have assumed here that there is no resistance. We have a simple LC circuit and there was no resistance, and we said that the total energy U was a constant. Now, if we were to take our LC circuit, let's go back here. If we were to take our LC circuit and we were to add a resistor in here, well, what's going to happen? The resistor heats up when it has a current going through it, and it dissipates away energy at a rate of I squared R. That means that the total energy here is not a constant in that case. If that's the case, then we can't say that this is equal to constant. It's equal to something else. It's equal to the rate at which energy is lost. In other words, we cannot say du dt equals 0. This would be energy per time. Oh, wait. Energy per time. Did you notice that? Energy per time. We've got another name for energy per time. That's called power. So it's not going to equal 0 if we add the resistor. So what is it going to equal? It's going to equal I squared R. That's the rate at which energy is lost. So that changes the solution if we do that. So we have d squared q dt squared plus q over LC is no longer equal to 0, it's equal to I squared R. And whenever we try to solve this one, we're going to get more than one solution, to be honest. We get a whole mess of solutions. Now, this looks frightening if you've never seen this before. But let me assure you, you have seen this before. You know how this works. You know the solution to this. You have a gut instinct for what this means here. And let me try to explain it to you by means of an analogy. You have been exposed to something called Hooke's law. Hooke's law says that if I have a mass, M, and that mass is attached to a spring, and that spring is attached to a wall, let's say right there, and I call this the equilibrium position where the mass just sits. Now I drag that mass out here. Maybe I drag it out to some maximum value of, I don't know, let's just call it plus x. Then if that spring is the type that will allow some oscillation, if I drag it out to plus x and let it go, it's going to go back here to position minus x. And if there's no friction between that mass and the floor, that oscillation is just going to go on forever. It would be a perpetual motion machine. Now you know that that's not a real life case, but you know, when in physics do we deal with real life? This is a mass oscillating back and forth because there's no friction here. All right, Hooke's law says that the force due to the spring is equal to minus k times x. K here is a constant. It's called the spring constant. And x is this distance along the x-axis here. The negative sign indicates that the spring is pulling back in the direction opposite of x. In other words, if I pull it out here, x is positive, but the spring is pulling in that direction. So the force due to the spring is in the negative direction. It's that way. But over here, when the spring is compressed, if x is in the negative direction, then the force due to the spring is going to be to the right because it's pushing it away. So that's what the negative sign indicates. It just indicates that the force is going to be in the opposite direction whether you've got positive or negative axis here. Okay, that's the force. Now I can rewrite that as F plus kx equals 0. Now force, you know, is mass times acceleration plus kx equals 0. And that's a second order differential equation. Even though you may not recognize it, that acceleration is a second derivative. So this is mass times d squared x dt squared plus kx equals 0. Now, does that look familiar to you? Well, let me go back here to this. That should look vaguely familiar. All right, if I were to divide through by the mass, there. Very similar form of equation. So if the form of the equation is the same, then the solution is also going to be the same. If I solve for x, it's going to be some max x, big X, times the cosine of omega t plus phi. And what's going to happen when I pull this back, I let go of it, it's going to oscillate back and forth. In other words, it's going to make a cosine. And this x, that's the max value from when I pulled it out here. That's the max. This will be the min. And it's going to go back and forth. I shouldn't say min. This is actually going to be the exact same value, except it's negative. So let's call it negative x max. All right, and it's going to become negative because the cosine becomes negative at times. So this is a description then with no friction. Now, what happens when you add friction? Well, without the friction, this is called a simple harmonic oscillator, and it will oscillate forever. When I add friction, then it becomes a damped simple harmonic oscillator. Damped simple harmonic oscillator. All right, so let's talk about what happens when you add friction then. When you add friction, the force at work here is still minus kx, but there's an additional force at work that's minus b times v. The b here is just a constant. It's a coefficient that's related to the amount of friction, but the velocity here is, that v is for velocity. I don't know if you've thought about it, but this term is for friction, and friction is proportional to the velocity here. So the total force that's at work is F plus kx plus bv equals 0. This is mass times acceleration plus kx plus bv equals 0. That means this is mass times second derivative of x dt squared plus kx plus b times dx dt equals 0. Let me rearrange the terms here. md squared x dt squared plus b dx dt plus kx equals 0. Now, my equation here and this equation here with no friction, you can see they're identical equations except for the middle term. The middle term is the one that's due to friction. All right, well, what did we have here? We've got this q squared dt squared. Okay, well, what about this? Remember what I is. I is dq dt. So there, the fact that this is no longer equal to 0 for our q, but is now equal to dq dt, this is where that second middle term comes in. So adding resistance is the equivalent of adding friction for this simple harmonic oscillator. Now, think about what the solution should look like. The solution up here was just a cosine, and it goes on forever. That's the solution, that's what we got there. But now we add friction. Intuitively, you probably know what this is going to look like. It's not going to go on forever, but it's probably going to start, if I pull it back, it'll start up here, go down, and then over time it'll quickly die down like that. So it starts at its maximum value up here of x max, goes to down here minus x max, and it eventually settles down and dies. Now, how quickly it does that depends upon how much friction is there. Is there a lot of friction or is there a little friction? If there's just a little, well, it maybe go on forever. If there's a lot of friction, it may do something like this. It may go, and then it's done. Or it may go something like that, and then it's done. So depending upon the amount of friction present, you're going to get multiple solutions to this equation right here. Now let's turn our attention back over here. Now we have not just a simple LC circuit, but now we've got an RLC circuit. And when we have an RLC circuit, it's no longer constant. The total energy is no longer constant.